everybody. I welcome all the participants in this simple lecture series. Firstly, I briefly introduce myself. My name is Muhammad Sharif. I'm a professor and head Department of Mathematics and Statistics at the University of Lahore. Here's the web link if you want to see the details of my credentials, but very briefly I'm mentioning here some awards, number of research papers, number of citations, H index, number of MPhil and PhD produced, etc. Let me briefly mention about the University of Lahore. We have at University of Lahore total number of faculties 11, total departments 50, total PhD faculty 350. In QS ranking worldwide, we are in 951 to 1000. We are at number 10 in Pakistan and number 2 in public private sector universities. Let me briefly mention about the Department of Mathematics and Statistics at the University of Lahore. We have currently 43 faculty members, out of which we have 23 PhDs. During 2024, we have published 249 publications in Q category. So, faculty publication ratio in our department is 5.79. We are currently running a BS Mathematics, BS Computational Finance, and from the fall 2025, we are planning to start BS Mathematics for Data Science. We are running the programs MPhil and PhD at weekend. We have the following groups at Department of Mathematics: gravitational theories and cosmology, biomathematics, fluid dynamics, graph theory, and fuzzy theory. Let me briefly introduce SIMPA, which stands for International Center for Pure and Applied Mathematics. This is a Category 2 UNESCO center based in Nice, France, with a mission to promote research in mathematics with developing countries. SIMPA is an association under the 1901 French law on associations and is funded by government agencies of France, Norway, Spain, Switzerland, and Germany. Well, I have been selected by SIMPA ICTP Fellowship in 2025 Research in Pairs. This call for 2026 is open nowadays, so anybody who is interested can apply, and the last date is April 2025. So the person who have been selected will visit some of the countries during 2026. In addition to the SIMPA Fellowship program, SIMPA has many other programs. For example, it provides funding to hold schools, SIMPA school in developing countries. It promotes SIMPA courses and many other things. So one can go for the details at the SIMPA web link. This is given by simpa.info. So after this brief introduction, I'm coming to the plan of my talk. This lecture series is a part of my fellowship program at Norway. So I have to deliver 4 days lectures, each lecture 2 hours. So this is the first lecture, and this will go by Thursday. So the plan of my talk is the following. I will touch basically the talk. I will discuss mainly the general theory of relativity. This is a obviously cannot be covered in 8 lectures. I mean 8 hours. But this is like a crash course on this course. And The distribution of my lecture will be the following. I will touch the following four topics: the Riemannian geometry, general theory of relativity, cosmology, and then finally I would discuss exact solutions by two different techniques. Number one, the Noether symmetries, and number two, the recently developed technique, the decoupling technique. Riemannian geometry is very well known that this is the language to understand general theory of relativity. But before going to the topic, I would suggest some books if anyone is can go into the details. The number one is written by Wald. This is the old book, but it is very fantastic, General Relativity. Number two, Stephanie Hans, General Relativity and Introduction to the Theory of Gravitational Field. This is also an old book, but you know the old is gold. These are very good books. Number three is also written by many renowned persons like Stephen Hawking, Kramer, McCallum, Hounslow, and Hart. Exact solutions of Einstein field equation. So this is a very good book, and it provides details, different techniques about the solutions, how to find solutions, what are the applications, etc. This is the latest version, 2003. And next, number four is the easiest book. This is for people who try to learn general relativity, Relativity Demystified. This is a series book, and it is available on different subjects, but in relativity you can understand many things from there. You can understand examples, etc. Number five is also an easy book, Fundamental of Special and General Relativity, written by Karori. This is also an easy book and provides examples, etc. And number six is Space-Time and Geometry and an Introduction to General Relativity. It is relatively recent book written by Carroll. And finally, I would like to mention Einstein General Theory of Relativity. This is written by Asar Qadir, a Pakistani author who is also my supervisor. We have sometimes in our coursework we have read this book. Asar Qadir has also written a special theory of relativity on the. So this is an extension of that book. All of these books are available, or you can check. Some books are available on the net, etc. I would like to mention particularly the most famous book, but maybe new generation doesn't know about that. That is the Gravitation. It is written by MTW, Misner, Hahn, and Wheeler. In our student life, we understand that this is the holy book of gravitation. It is a heavy volume book, and it is initially written was 1974. So, but I don't see nowadays it is available, or people can read it, but it is the book which contains everything about relativity and its applications. So, after mentioning these things, I would start my topic, the Riemannian geometry. You know, geometry is a combination of two words, geo and metry. Geo means earth and metry means measurement. So, it is in fact the measurement of earth, and Riemannian is the person who developed this theory, this geometry, because we all know about the Euclidean geometry, but this is a special geometry which is used in higher dimensions, etc. Again, to learn this geometry, we need to learn tensors. So, my first portion of the talk is about tensor analysis. So, I am going to start from the very beginning, because tensor is a generalization of scalar and vector quantities. So, I would like to define scalar and vector. Well, scalar is a quantity which is fully described by its magnitude, no direction at all. So, it is simply described by a single quantity. For example, we can say temperature is the scalar quantity, mass is the scalar quantity, energy is the scalar quantity, and many more. When we give direction to a scalar, it becomes vector. So, vector is in fact associated with both magnitude as well as direction. Its examples can be seen like speed is a scalar quantity, but if we give direction, it becomes velocity. So, velocity is a vector quantity. Similarly, force, momentum, etc. Now, tensor, as I have told you that this is generalization of the scalar and vector quantities. So, this generalizes the concepts of scalar and vector in higher dimension. When we talk about tensor, it means we are moving towards higher dimensions. It is used to describe physical quantities in a way that are independent of the choice of coordinates. So, in a simple words, we can say a tensor is a quantity which remains invariant under coordinate transformation. Coordinate transformation means if we have, for example, two different frames and the quantity remains same in two different frames, then we say that this is a tensor quantity. Now, we move forward. We define the rank of a tensor. Rank of tensor is in fact the index putting on the quantity. So, you know, scalar has no rank because it does not have any index. Similarly, if we talk about vector, you have single rank. Mathematically, the rank of a tensor is the sum of contravariant and covariant indices. So, if we have covariant index q and contravariant index p, then the rank of a tensor is the sum of these two. So, p plus q is the rank. So, scalar is a single number, so it has no index. So, it means it is a tensor of rank 0. Well-known example is the scalar field, which has no index. Rank 1 tensor is the vector quantity. It has one index. When we represent it in terms of indices, we have one index. So, contravariant vector has like this and one index, it means it has one rank. Covariant vector, we have put the index in the subscript. So, examples can be seen as force, we can represent in the following way. This is the index, and similarly we have put index here. So, we can put the vector with one index. Now, we generalize this idea. Obviously, genuinely tensor is the rank 2 tensor, it has two indices, and the well known example I would put the details later on is the metric tensor. Metric tensor has two indices, so it means it is a rank 2 tensor. We can extend this idea to the rank 3 tensor, and Riemann curvature tensor is the well known example of rank 3 tensor. Now, we define the symmetric tensor. We say a tensor is a symmetric tensor if its indices, if when we change the indices of the tensor and it remains unchanged, it means it is symmetric. For example, here we have given the rank of tensor 2, and when we replace AB by BA, it remains unchanged. And the well known example is the metric tensor. Metric tensor is a symmetric tensor. So, next we come to the symmetric bracket. This is obviously the idea coming from the symmetric tensor. We can define the symmetric part of the tensor as follows. Here round bracket indicates symmetry, and this can be written is equal to 1 by 2 factorial into AAB plus ABA. Here obviously round bracket means symmetry. We can extend this to antisymmetric bracket, antisymmetric tensor. This is also called skew symmetric if its components change sign when any two of its indices are swapped. For example, we consider a tensor of rank 2 here. Here you can see when we replace AB equal to by BA, we have minus sign. This minus sign is due to the antisymmetry property. If it is symmetric, then there is no negative sign. So we can say a well-known example is the Maxwell field tensor. This is antisymmetric tensor. Now we can define the antisymmetric bracket. Here is the definition of antisymmetric bracket. In case of symmetry tensor, we have positive sign, but here we have negative sign, and the notation of antisymmetry bracket is the square brackets. Next we come to the contravariant vector. In fact, contravariant vector means the index is upstairs or on the upside of the quantity. So a quantity whose components transform directly with the coordinate basis under a change of coordinates, then it is called contravariant vector. Here is the example AA. Similarly, we can define the covariant vector whose components transform instead of directly, inversely with the coordinate basis under change of coordinates. So in this case, we have covariant vector. And mixed tensor, in fact, we have both possibilities. I mean, a tensor with contravariant and covariant components transforming accordingly under change of coordinates. So it has two indices at least. So it is given by A, AB. Now we come to the proper definition or mathematical definition of the tensor quantities. Here first of all we shall define the contravariant vector. Suppose we have n number of quantities given by A1, A2 to An in a coordinate system x1, x2, x3 to xn. For example, we are putting these quantities in a frame which is denoted by, say, O frame, and then we consider another frame, O prime frame, and these are related to A1 prime, A2 prime, An prime. So in that coordinate system, we have the coordinates x1 prime, x2 prime, and so on, xn prime. Then we can write the transformation equations as given here. In fact, this is the transformation equation. You can see A prime P x prime, this is in O prime frame, and we are transforming this quantity to O frame. So this is given in O frame, and this x prime is O prime frame, and this x is in O frame. So in fact, we are transforming, or we are relating the two quantities A prime and O prime and O. Similar, if we can in fact omit that summation convention, and in that case we can simply write down this A prime P is equal to partial x prime P partial x q A q. This is very important equation in the sense that we use this formula when we transform from one system to another system. We can use similar definition to define covariant transformations. Here again we are writing the quantities in O frame and relating to O prime frame, but now we are using these quantities for covariant vector. So similar type of equation or formula is developed here, but here we are writing for covariant vector. So if we can define this transformation, then we say that these are components of a covariant vector or covariant tensor of first rank. This is obviously first rank because we have only one index. By the way, if you have any question, you can ask any time. You are most welcome. Now we go to the transformation coordinates for a tensor of rank 2. So, here we are considering n square quantities which are in AQS. QS run from 1 to n. So, they are again in O frame, and we are relating these quantities to another frame O prime, in which we have A prime PR, and these quantities are related by this. You can see here we have two indices, so we have two transformations. When we have single index, I mean vector quantity, we have single transformation. So, similarly, if we add the index, you can add here the transformation. So, here the n square quantities of AQS are called contravariant components of the second rank. Same idea can be extended to covariant tensor. We have just writing down the transformation equation with lower indices. Obviously, when we have two rank tensor, we can extend the idea to mixed tensor. Here, when we use the mixed tensor, that means A prime P OR is equal to when P is for the prime frame. So, we are using X prime P, and for here X prime R. So, this is a bit interesting that we are mixing accordingly. Here you can see that we have just put the prime here because this is covariant, and in case of contravariant we have put the primes in the upstairs, and here we are mixing for the primes upper and lower. Okay, now we come to the, after defining these quantities, we come to the some interesting game, that is free index. In other words, we can say that the index which appears once. So, you can see in this equation A is equal to B A plus C A. So, here A index is a free index. For the correctness of the tensor equation, we must have balanced indices on both sides of the equation. This is the first check to check the tensor equation. This means the equation holds for all values of A. A can have any value, for example 1, 2 and up to n. This represents a degree of freedom that does not remain fixed during calculation. Another index is the dummy index. This appears twice because it is dummy and it has to contract with some other index. So, it appears twice exactly in a single term of a tensor expression, once as an upper index which is called contravariant, and once as a lower index which is called covariant index. You can see in this equation here we have put A is equal to G upper AB B B. So, you can see here that here B is the dummy index because B is contracting with this B, and you can see both sides they have the equal indices. Obviously, the index B is a dummy index because it appears twice in the same term, once up and once down. The index B is summed over, so it is consumed in the computation. Now, by defining these two quantities, free index and dummy index, we can define the idea of raising and lowering of indices. In tensor calculus, raising and lowering indices refer to the process of converting covariant indices to contravariant indices or vice versa. So, in fact, this helps to invert the upper index to a lower index or lower to upper. This operation is performed using the metric tensor G AB or its inverse G upper AB. So, to raise an index of a tensor, one must multiply it by the inverse of the metric tensor G AB, as when we are raising, originally we have TB, a tensor quantity, or you can say vector quantity, and we multiply it by upper GAB and you can see that B is the dummy index, so it gets contracted, and we have obtained TA. For a tensor with multiple indices, only the specific index is raised. Here we can see that we have originally TBC, and you multiply it by GAC. T is the dummy index, and we are left with mixed tensor TAB. Now we can lower the index by multiplying the index tensor by the metric tensor. Here we multiply it, and here B is the dummy index, so we obtain TAB. We can extend this idea. We multiply it by GAC to mixed tensor, and we obtain the covariant tensor TAB. So this is the benefit of this metric tensor, that we can lower or raise the indices as we required. And this is required. I shall do the examples later on. Before moving further, we see a movie, video clips of the vector quantities.
Tensors are mathematical objects that transform in a special way when the basis vectors change. Understanding tensors is fundamental to understanding the curvature of spacetime in Einstein's general relativity. A tensor of rank 1 is a vector. Let's pick new basis vectors. We typically describe a vector by how many of each of the basis vectors we have to add together to produce it. But there is also another way to describe a vector in terms of the basis vectors. This is by taking the dot product of the vector with each of the basis vectors. For now, let us return to the typical way of describing a vector. Here, the vector has the components 4, 2, and 6. Suppose we double the length of each of the basis vectors. The components of this vector are now 2, 1, and 3, which means that the components have decreased. When we increased the lengths of the basis vectors, the components of our vector decreased. If we decrease the lengths of the basis vectors, the components of our vector increase. Because these two quantities change contrary to one another, we refer to this by saying that these are the contravariant components of the vector. Describing a vector in terms of the contravariant components is the way we usually describe a vector. Suppose we instead describe the vector in terms of its dot product with each of the basis vectors. If the basis vectors are of length 1, then the result of these dot products will be these 3 lengths. If we double the length of a basis vector, then its associated dot product will also double. When we increase the lengths of the basis vectors, the dot products also increase. When we decrease the lengths of the basis vectors, the dot products also decrease. Because both quantities vary in the same way, We refer to this by saying that these are the covariant components for describing the vector. We can distinguish the variables for the covariant components from variables for the contravariant components by using subscripts instead of superscripts for the index values. We can distinguish the variables for the covariant components from variables for the contravariant components by using subscripts instead of superscripts for the index values. Since these are just two different ways to describe the same vector, the same variable name is used, which in this case is the variable v. Suppose we have two different vectors. Let's call the first vector v and the second vector p, and let's always continue to use these names even if the basis vectors change. Suppose we multiply one of the contravariant components of v with one of the contravariant components of p. If we consider every possible way in which we can do this, we would get a matrix as shown. This is an example of a tensor of rank 2 with two contravariant index values. Suppose we multiply the covariant components of v with the contravariant components of p as shown. This will give us a different description of the same rank 2 tensor, with one covariant index value and one contravariant index value. Suppose we now instead multiply two covariant components from each of the two vectors as shown. This will give us a different description of the same rank 2 tensor with two covariant index values. What makes a tensor is that when the basis vectors change, the components of the tensor would change in the same manner as they would in one of these objects. A tensor does not necessarily have to be created from vector components, as is shown in these examples. A tensor of rank 1 is a vector. A tensor of rank 1 has a number associated with each of the basis vectors. In a tensor of rank 2, instead of associating a number with each basis vector, we associate a number with every possible combination of two basis vectors. In a tensor of rank 3, we associate a number with every possible combination of three basis vectors. A tensor of rank 3 can be composed of the combinations of components of 3 vectors. We can create different descriptions of this tensor by using different combinations of contravariant and covariant index values for the components of the 3 vectors.
Okay, if you have any question, you can ask, please. If there is no question, then we come to the examples. First, we have learned about the coordinate transformations. The first example is coordinate transformations. Here we are transforming the metric tensor in Cartesian coordinates to polar coordinates. So, the relationship between Cartesian and polar coordinates is given here. That is x equal to r cos theta, y equal to r sin theta. And then we can find the r and theta in this form. And obviously, we can write down the transformation matrix as follows. And its inverse is given by this formula. And now we can calculate these entities from here 3.31, and then we can use the transformation formula. This is given as GAB prime is equal to partial x C partial x A prime partial x D partial B prime G C D. So, in fact, this depends upon the new coordinates and this depends upon the old coordinates. And we know that x is equal to r cos theta, y equal to r sin theta, and this implies, these two implies that r is equal to x square plus y square and theta is equal to tan inverse y over x. So, we can calculate these transformation matrix from this, and then we can write down, for example, we know that this value is equal to 1 0 0 1 in Cartesian coordinates. And when we calculate these things, I just calculate one component, that is So we know that GAB is just 1001. So we can have only non-zero in the diagonal form. So partial x1 partial x1 prime partial x1 partial x1 prime G11. Similarly, we can have partial 2 prime partial x1 prime partial 2 prime partial x1 prime 2 2. Rest of the two components will be 0. So inserting these values, and then finally we can get the result GAB prime is equal to 100 r square. So in fact, this is metric is given in Cartesian coordinates, and this is in polar coordinates to this process. Okay, we have in fact found the metric tensor in polar coordinates. Similarly, we can extend this criteria to 3 dimension. If we want to change the metric from Cartesian coordinates to spherical polar coordinates, we define the transformation coordinates from Cartesian to spherical polar. Then we write down the transformation equation, and then we can write down the transformation matrix, and then we can find the values of these, and this is the required metric in spherical polar coordinates. To find the inverse is very simple for when the metric is diagonal. Say if it is diagonal, for example, AB prime is equal to 100 over 0 r square 0 r square sine square theta. This is the metric in spherical polar coordinates. We can just write down its inverse in a very simple way, 100, and just inverting r square by 1 r square, 1 over r square sine square theta. So it is very simple only when it is diagonal, but even if one element is non-zero, then we have to go by some other technique, for example, like using the adjoint method. Okay, in this example, we raise and lower the indices of a vector. Here you see that this is given as the metric in polar coordinates. Its inverse is simply written like this, and we want to find, we are given that vector in the upper index 1 1 and vector in the lower index 0 1. We want to find the other way around, that we want to lower the indices and raise the index of this vector, and finally we will calculate the product of these two vectors. You know the formula by this is in the upper index. So we can lower the index by multiplying with the metric tensor GAB, and here when you have the formula VA is equal to GAB, then you can calculate its R component as G R B V B. Now, because you are given the metric as polar coordinates, so you have the option of R R V R plus, there is no other option, because when you put the other options, the result will be 0. So you have 0 here. So it is R R means 1 and V R means 1. So the answer is 1, V R. So this is given here. Similarly, you can calculate V theta, and the final answer is 1 r square. So you are given in the upper index 1 1, and you have lowered the index, and you have found that 1 r square. On the similar lines, we can raise the index by using this formula and using the same procedure, and you can find that the vector with upper index is 0 over 1 over r square. And product can be found in this way, that v dot w is equal to GAB VA VB, and just open it with values G00, G11, and then inserting the values from the metric tensor as well as vector, and you have found the value 1 here. I mean, the product of these two vectors is 1. The other way can be found like this. For example, v dot w can be written as VA WA, because A is here dummy index, though they can be contracted, and just write down and the final answer will be the same as to this method. So this is a very simple example to find to lower and raise the indices. Next example is bit technical. Here you can see that you are given the metric like this, and you first write down the metric tensor and its inverse. Here you see that the metric tensor is GAB is equal to x square minus 1 1 1. This is the metric tensor. However, to find its inverse is not simple because it is off diagonal metric. So in order to find its inverse, there are two ways. The first way is, I mean, you want to calculate GAB. So the first way that is given in this book is just multiply XX, XY, YX, YY with x square 1 1 minus 1. This is the inverse which we want to find, and this is the original matrix, and it should be obviously equal to unit matrix. And solving this system, you can find this value. So inverse can simply be found as I show you. GAB is equal to adjoint of GAB over determinant of GAB. So adjoint of this is minus 1 x square minus 1 minus 1, and divide by its determinant, which is minus x square minus 1. So you can write down 1 1 is equal to 1 over 1 plus x square, 1 2 is equal to 1 over 1 plus x square. This is also 2 1, and 2 2 is equal to minus 1 over minus x square 1 plus x square. So this is a simple way to find the inverse of this matrix, because this is off diagonal, and you can now calculate these things. You are given here this vector, and you have calculated the metric tensor with its inverse, and finally you can calculate its component 0, and so y component as 1. So the resulting solution will be 0 1. Similarly, we can lower the index with this formula, and you can calculate this value by some steps. It is not very difficult. You can calculate. We come to the next example. This is also for lowering and raising the indices, but it is in 3 dimension in spherical polar coordinates. It is also straightforward because we know that the metric tensor in spherical polar coordinates is 1 0 0 0 r square 0 0 0 r square sine square theta. This is the metric tensor when we say that this is spherical polar, and its inverse can be written very simple because it is it is diagonal, so we can write its inverse as follows. Now, using these two matrices, we can calculate x a as well as y a in a very simple way. We first calculate the xr component, then x theta, then x phi, and you can see that the answer will be 1 r cube 0. Similarly, we can raise the case. Okay, any question up to now? Because we are going to second section, which is a bit more technical. Up to now, we have very basic concept, and now I shall come to the concept of manifold. Okay, manifold is combination of two words. Many means several, fold means layers. So, an object with several layers is called a manifold. So, in mathematics, a manifold is a fundamental concept used to generalize and extend the notion of curves and surfaces to higher dimensions. So, this concept is usually used for higher dimensions, but for the sake of understanding and examples, we start with one dimension. This is in technical definition, in fact, involves the topology. So, manifold is a topological space N which resembles with Euclidean space R raised to power n locally, but may have a different global structure. So, you can say that locally it corresponds to the Euclidean space. Now, we come to the Riemannian manifold. Riemannian manifold is a combination of manifold with Riemannian metric. So, this is a differentiable manifold with Riemannian metric, which is a smoothly varying positive definite inner product on the tangent space at each point of the manifold, say P. Now, a very simple example is the straight line. Straight line is the simplest example of one-dimensional manifold. We can extend it two-dimension when we consider the plane. So, the Euclidean plane is a two-dimensional manifold. Next is the circle. Circle is a one-dimensional manifold. Though it is a closed curve locally, it looks like a line. Similarly, we can extend it to sphere. A two-dimensional sphere is the set of points equidistant from a center in 3D space. Locally, it corresponds to a plane in two dimension. We can extend this idea to n-dimensional space. So, for any n, the n-dimensional sphere is defined as the set of points in R n plus 1 at a constant distance from the origin. Manifolds are very useful in different places. For example, in physics, we use this concept in space-time in general relativity, and this is usually used as a four-dimensional space-time with a Lorentzian metric. But in other places, these are very important objects, particularly in modern mathematics, and are used extensively in physics, computer graphics, and data analysis. We all know the concept of derivative in flat space-time, which is usually called the ordinary derivative. But when we talk about the derivative in curved space, it is not simple. So, it is easy to move vectors from one point to another in flat space. They transport parallel. However, it is not easy in curved manifold. So, for this purpose we need to use Taylor series and generalize derivative on curved space. So, the covariant derivative of a contravariant and covariant components of a vector are defined mathematically as follows. Here in the first expression we are in fact defining the covariant derivative of the contravariant vector with respect to B. Here semicolon indicates the covariant derivative, and you see here when we have only one index, I mean we are taking the contravariant the covariant derivative of a vector, we have only one term extra. This is the extra term, and this is the usual derivative, which is in fact the covariant which is the ordinary derivative of a contravariant vector with respect to the same index we are taking, but this is the extra term. And you can see this this term involves the Christopher symbol I am introducing the first time. Here if we are discuss this concept on flat space, this Christopher symbol will be 0. For example, we consider the Minkowski space-time. Minkowski space-time we have constant metric potentials, so the derivative will become 0. So, this Christopher symbol will be 0. So, it means it reduces to the usual derivative when we talk about the flat space, but here we have the extra term. And similarly, we have the covariant derivative of a covariant vector, but the difference is only the negative sign. So, for the contravariant vector we have positive term, for covariant vector we have negative terms, and as the number of indices are increased, then the number of terms will be increased. Here we have already told that this is the Christopher symbol, its definition is given here. This is the 3 index symbol, and this involves the derivative of the metric tensor components. And interestingly, this is a symmetric symbol because the metric tensor is a symmetric quantity. Now, if we extend this idea to 3 rank tensor, you can see this is the ordinary derivative, and because we are applying this idea to 3 index symbol, 3 rank tensor, we have 3 additional terms. For the upper index we have positive sign, for the 2 lower indices we have negative sign. If we use this definition of the covariant derivative, it can easily be verified that the covariant derivative of the metric tensor is 0. And if we write down these 3 equations and solving these 3 equations, we can calculate the expression for Christopher symbol. Perhaps some people may think how this can be 0. This can be easily verified. If we insert the values of the value of Christopher symbol here and value of Christopher symbol here, and then solve this equation by opening it, then you can, for example, I just write down one expression, G BC semicolon D equal to 0. So, this is the equal to BC D minus EDB GEC minus GBE EDC. So, what we shall do? We shall insert the value of the Christopher symbol 1 by 2 G E A, introduce a new index, and then D A comma B plus here it should be D comma D A comma B, B A comma D, minus dB comma A. Similarly, putting here minus GBE and value of Christopher symbol, and then you open it, cancel out each term, and the result will be 0. So, in this way we can verify this expression, this one. Next concept is the Lie derivative. We can define the Lie derivative of some quantity, say metric tensor, with respect to the vector as follows. Here we are taking the Lie derivative of alpha with respect to xi. Lie is the person who defined this derivative, and you can have in this way. Obviously, alpha semicolon A is the covariant derivative, and if we simplify, if we open this covariant derivative and then simplify the expression, we can arrive finally this expression, and this is very useful for the purpose of examples. Okay, now we can make some comments about these two derivatives. We have seen that covariant derivative is a metric dependent tool for analyzing changes in tensor fields while preserving geometric structures. I mean, covariant, we see that covariant derivatives involve the Christopher symbol, that means the metric tensor. It is crucial for curvature analysis and geodesics. We shall use this definition in geodesics as well, and this depends upon the Levi-Civita connection, which is the Christopher symbol. It maintains metric compatibility, while the Lie derivative is a tool for measuring the deformation of fields along vector flows. This is essential for symmetry and flow analysis, because this is useful for the symmetry purposes, like we can define the Noether symmetries, we can define the killing vectors, etc. We will discuss these concepts later on. This does not depend on connection, while it is intrinsic to manifold geometry. Even it does not preserve the metric, because this directly does not involve the metric tensor. Here are examples of, first is the Lie derivative. Well, here we are taking the mixed tensor or two-rank tensor. This is the two-rank tensor for which we are to calculate the Lie derivative, and we are calculating the Lie derivative with respect to this vector. As you can see from this example, we are taking the coordinates P, Q, R. So, we are just for the sake of simplicity taking x1 is equal to Q, P, x2 is equal to Q, x3 is equal to R. So, this is the formula when we open for the second rank tensor. The Lie derivative of this mixed tensor is given as follows. We have three terms here, and for the sake of simplicity we denote it by lambda AB. We can denote it by any quantity. For example, we can write down A, AB. Now we calculate this. Here, say we take, we have here 1, 2, 3, three in coordinates. So first we calculate lambda 1, 1. So we are just taking, first of all, A equal to B is equal to 1. Then we take accordingly where it is fixed. We have fixed 1, 1, but we can change here C. So, C here is 1, 1, then 2, 2, then 3, 3, then come to here again we have given the variations 1, 1, 2, 2, 3, 3, and finally the third term. So, when we insert all the values from this mixed tensor and the vector and simplifying this, we can have the answer 2pr plus qr minus 2p square minus pq. So, this is the way we can calculate the Lie derivative for any given for any given tensor with respect to some vector. We can further move its components 1, 2. Again, we have fixed 1, 2, but we can change the other values accordingly, because we have all 9 components here and 3 components here. So, in this way we can calculate all the components. These are the all are non-zero components. We move on to another example, which is in fact the covariant derivative of the tensor coordinates. This is again in spherical polar coordinates. We can see from the mixed tensor that it is written in spherical polar coordinates r theta 5. So, it means because we need to write down the metric tensor for covariant derivative. So, this is understood that we are taking the metric tensor of the spherical polar coordinates. Further, we need a tensor quantity for which we are calculating the covariant derivative. So, this is the formula of covariant derivative of this mixed tensor. In fact, this is the ordinary derivative, and because we have 2 index tensor, I mean mixed tensor, so we need 2 more terms. The first positive term is due to the upper index, and this negative term is due to the lower index. So, this is the general formula, and we can just assume that this is equal to B A B C. This is just an assumption for the sake of simplicity. So, now we calculate say B11. Here we put B1 comma 1, and this is in fact comma, not 1 1. Here it is 1 1 comma 1, and calculate the rest of the things. We can see from the upper indices, non-zero indices, non-zero Christoffel symbols, that they make these terms equal to 0. So, we are left only the answer from the first term, that T11 is this thing. So, differentiating this T11 with respect to r, we have cos theta. Similarly, we can calculate rest of the terms. For example, if we find B112, then we put here 1 1 comma 2, because we say that B1 1 2 is equal to T1 1 comma 2 plus 1 2 2 2 1 2 1 2 T1 2. So, T11 is this thing. If we differentiate it with respect to 2, then we have minus r sin theta, because as you know, 1 corresponds to r, 2 corresponds to theta, 3 corresponds to phi. So, this means we are here with minus r sin theta, plus 1 2 2 here, it is minus r, and 2 1 is sin theta sin phi. And last term 2 1 2, 2 1 2, we can see from here it is 1 over r with T12. T12 is AR sin phi. So, this r can be cancelled, and we are left with minus r sin theta, and we arrived this result, this one. So, in this way we can calculate all the terms, but I am not going into the details. You can calculate Okay, we come to another example. I think this example is again about the, this is about the Christopher symbol. We have calculated already about the Christopher symbol, but this is the example of a, in fact, we are taking 1 0 0 0 r square 0 0 0 r square sine square theta. This we know already know, this is the metric tensor in spherical coordinates. But if we take radius constant, say we take r equal to a on the surface of a sphere, then this reduces to, instead of 2 dimension 3 dimension, 2 dimension. So we can take it 0 a square sine square theta. So this is the metric on the surface of a sphere of radius a. So for this case, we can calculate all the Christopher symbols. Here they have used different notation for the Christopher symbol. This is the curly bracket. Some books or some people use this notation. So this is again the Christopher symbol for the metric in 3 dimension spherical symmetric coordinates. So all non-zero coordinate Christopher symbols are given here. Before closing today's lecture, I would like to discuss any questions, comments for today's presentation or lecture. We shall resume our tomorrow's lecture from this.
Sir, I want to ask that what is the significance of Lie derivative in general relativity and how it is related to killing vectors?
In fact, Lie derivative was defined by Lie, the very famous geometric person, and this, its significance in the sense that we use this Lie derivative for symmetry purposes. I mean, we define the symmetry to killing vectors. I will discuss this in detail when we discuss the symmetry or killing vectors, and also for Noether symmetries and so on. So it is in fact used for the purpose of symmetry discussion, where, say for example, if we take the Lie derivative of the metric tensor is equal to 0, this means we obtain the killing equations and we can define the symmetry. I shall discuss in detail when its application will come for tomorrow's lecture.
Yes, sir. Okay. Thank you, sir.
Try your question, sir. Sir, previously you discussed about manifold symmetry. Can you explain about that?
Well, I have given manifold, as I told you. This is a structure of several layers. The simplest example I have given the straight line. This is the simplest. But when we talk about 2 dimensional, 3 dimensional, we can go to the sphere and even n dimensional. So this is the description of the figure in n dimensions in general, and technically it is defined through topological space. I mean, it holds, it preserves some topological properties. Okay, I have written that it covariant derivative preserve the properties of metric tensor. Metric tensor, as we know, in the definition of covariant derivative, metric, it is defined through metric tensor because it involves Christopher symbol, and Christopher symbols involves the metric tensor and its derivative. This is the reason we say that this preserves the metric properties. When we say about the curvature properties, in fact, metric tensor is the basic ingredient from where we start everything. I shall discuss about curvature tomorrow's lecture. We define from the metric tensor Christopher symbol. Then Christopher symbol is used to define the covariant derivative and the curvature tensor. Then some other tensors like wild tensor, etc. And for this reason, we say this covariant derivative, since it involves the metric tensor, so it preserves all the properties.
Okay, sir. Thank you.
You are motivated to ask questions because, in fact, this is basic lectures and mean to like graduate students, undergraduate students. Okay, if there's no question, then we close today's session, and we shall start off from the same place where I left this lecture today. Thank you very much.